Hello, um, my name's Esther Banaian, and I'm talking today about some work that I started about 2 years ago at this point with Elizabeth Kelley. We are both grad students at the University of Minnesota. I'm really excited to be talking about it. We have an archive preprint, which you can find by this number, or if you Google the title of this talk, it's almost the title of the paper. And there's also a FIPSAC abstract if you want something a little shorter. Okay. So this talk, like any good talk, the background will define the words in the title. So we'll talk about snake graphs, which really requires us to talk about cluster algebras from surfaces. We don't have time to do a full definition of cluster algebras. That can take a long time, but after this, if you would like to Google them, there are some very nice survey materials. And then we'll talk about what we mean by orbifolds, since we're going to take the surface story for snake graphs and put it into orbifold land. And so then once we define orbifolds, we'll be ready to launch into snake graphs and orbifolds put together. Okay. All right, so snake graphs are a combinatorial tool used to study cluster algebras from surfaces. So let's think we'll have to talk just really high level about cluster algebras. So cluster algebra is an algebra. So we think about the generators, and they come in overlapping sets called clusters. So here we see the word cluster. We'll see an example in just a second. So the clusters will contain the generators, and they'll be related to each other by a process called mutation. Okay, so those are just some keywords. So without giving you all the definitions, here are some clusters for a cluster algebra of type A3. So again, and the elements, the individual, these are all the raw polynomials. They're all rational functions, but just one term in the denominator. These are called cluster variables, the individual elements, like x2 plus 1 over x3, that's a cluster variable. So each cluster is the same size, and I've embedded this onto like a 3 regular graph. So at each cluster, I can mutate, and of course I didn't draw all of it. I can always mutate in one of 3 directions. And when I mutate, I take just one cluster variable and I replace it with something else. The thing I'm not really telling you is how to know what to replace it with. To really do that, we'd have to actually carry along some extra information, either through a directed graph, which usually we call quivers when we talk about cluster algebras, but it's just a directed graph, or more generally, a skew symmetrizable matrix. So that would be giving us the recipe for how we mutate. But yeah, so we just, again, high level dynamics, we have all these sets at the same size. We can replace one element in each set. This replacement operation is an involution. So this is not my tree here is not directed. Sometimes the mutations commute and sometimes they don't, kind of depending on how close or far the variables are and such. So now I'm going to show, so in motivating cluster algebras from surfaces, I can kind of make the same sort of picture, instead using triangulations of a surface. So when I say surface, I'm going to think about the surface has a certain special set of marked points. And those marked points are the places that are allowable start and end points for arcs. So when we define a cluster algebra from a surface, the arcs on the surface are going to be representing the cluster variables. And then clusters are going to correspond to triangulations. So triangulations are like special sets of arcs, right? A triangulation, you want all your arcs to not cross each other, and you want to be a maximal such set of non-crossing arcs. So we have some pictures here. A lot of examples of triangulations of a hexagon. So the vertices of the hexagon are like the special marked points that I can connect. So here we're just looking at diagonals of a polygon. And then the thing that works for mutation when we have triangulated surfaces is what we call like flips of an arc. So for instance, if I look at these 2 adjacent triangulations, I can remove the arc labeled 3, and then I can replace it with a unique other arc, right? Because locally 3 is a diagonal of a quadrilateral right here, and every quadrilateral has 2 diagonals. So here we see the dynamics of flips in triangulations acts a lot like the cluster mutation. But we can dig even deeper, and we do this through the Ptolemy relation. This is how we can actually take an arc and spit out one of these Laurent polynomials that we saw in our intro example. So the Ptolemy relation is, first and foremost, a statement about lengths of arcs. So it says that given a quadrilateral, sufficiently nice, you want all 4 vertices to be able to fit on a circle. So not too crazy of a quadrilateral. If you take the product of the length of the 2 diagonals, so here I'm calling them x and x prime, I can write that as a sum of lengths, or a times c and b times d. So a binomial in terms of lengths of the outside. And if I'd given you proper definition of cluster algebra, you would see that this looks a lot like what cluster algebra mutation is in general. Oh, I just realized my video might be covering up in the recording. Maybe not. Okay. So we can use this relation to, given an arc, okay, well, let's just start from the beginning at this bottom example. So we need to pick like an initial triangulation, and that's what I've labeled 1, 2, 3. And you do this with cluster algebras too. You have an initial cluster. But then we just take any other arc. So it's probably going to cross some arcs in the triangulation unless it's already in the triangulation. And I can use this Ptolemy relation to recursively resolve crossings. And then someday I will have like the full expansion of the arc. So I've labeled this arc gamma, and we can resolve its crossing. First, we'll start with resolving at 2, but what I pick first doesn't matter. So for instance, if I first resolve the crossing this way, I get the first picture. So one thing I pick up is the arc x1, which is already in the triangulation. And then I pick up another arc that does cross arcs in the triangulation, but it crosses one less. So I'm making good progress. And then if I resolve the crossing the other way, I simply get 2 boundary arcs. And I'm setting those equal to 1. I could record variables for my boundary, but just to make it easy, I'm setting them to 1. So then I do the same process for beta. I pick up, so now beta only crossed 1 arc, so everything I pick up is already in the triangulation or on the boundary. So first of all, I know that beta times x3 is x2 plus x1, and then plugging that back into x gamma, I recover an expansion for x gamma. And we saw that term here and here in this initial tree, and then we saw that arc here and here. They had different labels, but that's okay. So now we see that this matches what it should. Okay. So what snake graphs do is they streamline this process, because this process and cluster mutation in general, this sort of recursive thing, it's not always clear what's going to pop out. So snake graphs are, the perk of the snake graph formula, which we're about to explain, is that you know a lot better what these expansions look like. In particular, this showed up as a proof of positivity, which has been a hard thing in general to prove for cluster algebras, that the expansion that you have when you do this mutation process maybe many times, that it's all positive coefficients. Okay, so now, given that same arc gamma, instead of doing that recursive process, I can just write down this graph. And this graph sort of locally looks like the parts of the triangulation gamma cuts through. So we get 1 square tile for every arc we cross. And then we label it with kind of the quadrilateral around that arc. So for instance, 3, again, the quadrilateral around it's mostly boundary arcs, but then we have the arc labeled 2, and that looks just like that. And then since gamma crosses 3 and then 2 consecutively, and this is a triangulation, that means 2 and 3, right? They border the same triangle. So then there's this third edge to that triangle, and both the tiles corresponding to 2 and the tile corresponding to 3 have that edge. So this boundary edge corresponds to this arc here. So then we glue those 2 tiles together. And for instance, if I instead also crossed 1, I would put a 3rd tile here. All right, so given this graph, then I simply enumerate all of the perfect matchings of that graph. So perfect matching as a subset of the edges, so that every vertex is incident to exactly one edge in that subset. So this graph has exactly 3. I've highlighted them on the right, and I've recorded the weights, where I just multiply together the weights of all the edges that I've used. Again, setting to 1 things that are unlabeled because those are just on the boundary. And the theorem is that your expansion of your arc is simply this weighted sum of perfect matchings in the numerator, and the denominator is simply the arcs you cross. So here we just cross 2 and 3. Okay, so that's the main snake graph formula. Now let's talk really quickly about orbifolds. So for us, when we say orbifold, we'll take a surface, but we're also going to have a special set of points called orbifold points. So each orbifold point has an order. We don't really mark it on the surface itself. We just kind of know on the side the order of each thing. We set the order greater than 2. There's a lot of good work on orbifolds where the points all have order 2. And our work would transfer over to that, but we just set it greater than 2 for some convenience. So the order, what the order reflects is that when you come to the orbifold point, you could, for instance, wind around it a while. But if it's order p and you wind p times, that's the same as not winding at all. I think you have to be a little careful how you index winding, but that's the rough idea. So there's like this mod p symmetry around it. Because if this was just a normal marked point, then every winding would be distinct. Okay, so then when we triangulate an orbifold, we're going to have special arcs to the orbifold points. Those are called pending arcs. So since triangulations are maximal, we know for sure that we need exactly one pending arc to every orbifold point. So here we have 2 orbifold points and 2 pending arcs. We draw them like loops. Some people draw them just like a line straight to the orbifold point. But I find it a little more useful just for what I'm doing here to draw the loop version. But we'll see why both might have their merits. Okay. So these pending arcs, right, they look a little different from a normal arc. And the rules end up being a little different too, which actually orbifolds correspond to something called generalized cluster algebras. And this is essentially why. So when we mutate / flip an arc, the Ptolemy relation is this 2-term thing. This 2-term relation, and like I said, it looks a lot like normal cluster algebra mutation. However, and we will go in a little more detail as to where we get this relation on the right, but when you mutate your pending arc and you check the lengths using some geometry, they're actually related by a 3-term relation. And again, notice that so every pending arc is locally going to be inside a bigone, right? Because like this, for instance, if you just had Z, A, and B, that would make a triangle right there. So we have just a bigone around it, but we have a 3-term relation. And this is where the order of the orbifold point matters. So we get this term lambda p. So lambda p is a scalar. It's 2 cosine of pi over p for your order p. Here's the first couple values, which the first couple are nice, and then they are less nice afterwards. And right, if p equals 2, then this is 0, which is part of the reason why the p equals 2 case is a little special. But that is also, it also works out in that case. That's still a valid thing you can do, but then you don't have 3 terms, you're back to 2. Right, so you might wonder where this comes from. And indeed, it comes from the normal Ptolemy relation. But it's helpful to look. So what we're going to do is we'll look at this mutation in the cover, or in a cover of the picture. So on the left, I have a triangulated orbifold. There's 3 marked points on the boundary, and I have 1 orbifold point. And I'm going to set that to be order 4. Oh, I have a random line in here, I'm sorry. Right, so if I were to mutate that green pending arc, I would get another pending arc there. Oh, right, I guess we haven't talked enough about the picture before we start mutating it. So in the cover, so this is order 4. So I have this picture, so I have 4 copies of everything. The pending arc kind of unfolds into a quadrilateral because it's 4 That's all connected. And then I see I have 4 copies of everything else kind of off to the side. And this is set up so that if I, center here and rotate 90 degrees, I get the same picture. Okay, so then, now you'll hopefully believe that if I were to mutate my pending arc, so that it's now instead based at 2, that would give this, that would have this in the cover. So what I can do then, so if I want to kind of get this generalized Ptolemy relation from what I know about just the normal Ptolemy relation, I just take one copy of that and kind of do normal Ptolemy relation. So notice it crosses 2 arcs, not 1, which is a reason why we get the 3 terms instead of 2. And then we pick up this lambda p because, right, this picture isn't quite triangulated. So that might make you a little uncomfortable because everything's been triangulated so far. But we can think about this polygon in the middle, and right, if this was a bigger order, it'd be a bigger polygon. So we think of it as a regular polygon because every side corresponds to the same thing in the orbifold. So you're going to pick up, say, when you do the Ptolemy relation, you're going to pick up an arc like this, and this lambda p, the 2 cosine of pi over p, corresponds to the ratio of what I call a 2 diagonal, which is like the shortest non-trivial diagonal in a polygon, and just the side in a regular polygon. So again, from high school geometry, right, a square with all sides have length 1, the diagonal has length squared 2, and that's lambda 4. So that's where the lambda p shows up. Okay. So now we're able to really get to the snake graphs from orbifolds. So first we introduce, so the big new thing we do is we can have arcs that are interacting with the pending arcs, and those are going to need slightly different rules. So thinking just quick again about the normal snake graphs. For instance, if gamma was just this arc on the left, its snake graph would just be 1 tile. And that would, that looks like the same picture we keep drawing for the Ptolemy relation, and it sort of encodes that. But of course, if gamma just crosses E but does other things, then we would have this tile as well glued onto other tiles. So when we interact with the pending arc, we introduce a tile that encodes the generalized exchange relation. So this is this hexagon I've drawn. It is kind of just like 2 square tiles put together, but I think the hexagon is nice because it should suggest something new. And this hexagon has 3 matchings. 2 go along the boundary, and 1 uses that middle edge with the label lambda p. And the way I've written it down, so every matching has a factor of c, and I've labeled this as if there's 2 tiles c. And so then we cancel and we actually just get 1 c in the denominator. So here we see how it's kind of just like crossing once because we just get 1 c in the denominator, but in the picture it kind of looks like I'm crossing twice. But in particular, when you do this snake graph expansion, or when you take the snake graph formula on this graph, you get the generalized exchange relation. So again, if gamma just crosses C and does something else, then I include this. This is just one of the tiles I use in a series of tiles. And the next example shows this well, I think. It's a pretty big graph, so you might not have time to look at all of it unless you pause it. But if we follow, gamma crosses C, then A, then C, then B, then C, then A, then C. And you can see that here. This would have many perfect matchings. I don't know how many, but here's an example, and then you could find all of the matchings, and that would give you the expansion of gamma. Okay. So we have a few kind of special cases. Well, yeah, maybe they're not special, but they're different from what we've been talking about. So far, we've just been talking about arcs. We assumed no self-intersections. well, I guess we didn't say that, but we were thinking about arcs that show up in triangulations. And those, triangulation, you don't want any intersection amongst the arcs. So you certainly can't have an arc that already intersects itself. That would be immediately kicked out of the triangulation. But these arcs can appear in surfaces that are more complicated than a polygon, and they can appear in the orbifolds as well. We've talked a little bit about how you can wind up to p minus 1 times if your orbifold point has order p. So we can build up a little more intuition for these arcs, looking again at a cover of an orbifold. So I have a pretty simple one on the left, a pretty simple orbifold. So remember, like the pending arc that starts at 2, for instance, would correspond to 5 copies of an arc here that, they don't cross each other. However, if I took an arc and wound around like that, that would correspond to all this collection of arcs. Makes like a star. And those intersect like each other there. They don't intersect themselves, but you take them all as one unit. So you see the self-intersection on the right also. You can also see here why we can only wind finitely many times around, because there's only so many different copies of 2 you can go to before you, for instance, don't go anywhere or go back to something like, 6 windings and 1 winding would take you here, I guess, depending how you count winding. So notice that these arcs that would have self-intersections, such as this, again, we're cutting through this cover where we have this polygon in the middle, this regular polygon. But unlike when it was from a pending arc, we're really cutting through the middle. So we're going to get just a slightly different kind of tile for arcs like this. Okay, so that's what's on the left. Let me zoom in just a little bit, because it's kind of small. So we end up having 2 different diagonals inside this hexagon, which is a reason why I wanted to draw the hexagon in the first place. And the labels are given by these normalized Chebyshev polynomials evaluated at lambda p. And they show up for the same reason that we originally had lambda p. These are encoding ratios of lengths of arcs in regular polygons. So they're not maybe as fancy as they look. Yeah, these are slightly normalized from how you might see Chebyshev polynomials if you just look them up on Wikipedia to get the right relationship. Yeah, so this would correspond to an arc that had k self-intersections around the orbifold point. And again, I can just use this as a tile in a bigger example if I'm just coming in, doing this, and leaving. And see a few more notes. So if you set k to be 0, you will recover the tile we started with for arcs without the self-intersection. And but in general, this picture has 4 matchings. Again, 2 boundary matchings. Then I have 1 for each of these long diagonals in the middle. Okay, so we can use these tiles the same way we use the other hexagon tiles when our arc has self-intersections. And then on the right, so this whole time we've been talking about arcs, so they had to start and stop at marked points. But we also can have like non-trivial closed curves in our orbifold. And if you're thinking about, say, the basis of cluster algebra, these closed curves are quite important. So we have a related construction for closed curves. We call them a band graph, because as you'll see, the graph ends up being either a cylinder or a Mobius strip, depending on maybe parity. But given a closed curve, we pick some starting point. And I wouldn't want to pick it, say, like the interior of the pending arc, because the interior only sort of exists, and it would be a little confusing. But we pick a starting point outside of pending arc, and then we pick an orientation. And then we make our normal snake graph as we normally would. However, since this is a closed curve, the first tile and the last tile will have an edge in common, like with the same label. So in this case, it's this edge and this edge. And those both correspond to the unique boundary edge in this picture. So then we just identify those edges. So our graph will be a little different. It'll be cylinder or Mobius strip. And after that, we take perfect matchings after that identification. So they'll look a little different. For instance, one perfect matching looks like this. Right, so we didn't have to do anything for the top, because once I match these, I've also matched the top. So there's a related formula or theorem, both in the surface case and now for us also in the orbifold case, that we can record our expansion of the closed curve with these matchings on the band graph. Okay, so there are more details to what I've talked about, such as if you're familiar with snake graphs, you can associate a second set of variables to them with the y variables, which you record by, one way to record them is to take all of your perfect matchings and you can put them actually into a poset, and recording height on the poset and how to get between different matchings of the poset picks up the second set of variables. And that all works fine here also. If you're interested in something like that or other details, I'd encourage you to look at our preprint. But thank you so much for watching. I really enjoy talking about math I like. Please email me if you have any questions or comments or really anything at all. Thank you.